Let's review work and energy. So I've got the equations here for work and energy. Work is equal to F dot S. Remember, in terms of a dot product, that means F times S times the cosine of theta, where theta is the angle between the force and the displacement. Your purpose of that dot product is to put the vectors in the same direction, and that can be a shortcut to the math when you remember that purpose of what that dot product is. In general, the quantity of work, okay, that is basically the thing that can change the energy. In comparison, force is the thing that causes an acceleration. Impulse is the thing that changes momentum. Torque is the thing that changes rotational motion. Work is the thing that can change the energy of an object. So you have work done if you have three different things. You have a force, you have a displacement, and those are either in the same direction or there is a vector component that is in the same direction. So we have the regular formula, we have the calculus version, integral of f of x dx. Okay, because it's an integral, you can also think of it as the area under the curve for a force versus displacement graph. Work can be done to change energy, so we can think of work being done to change kinetic energy. That's oftentimes a shortcut in analysis and problem solving. If you're thinking in joules, the joules of work change the kinetic energy. If those joules are being done expressly to speed an object up or slow an object down, by the same idea, we could also say that work is equal to change in potential energy. For example, if you are lifting an object up, the joules become joules of gravitational potential energy. If you are stretching a spring, the joules become joules of elastic potential energy. Okay, and we'll talk a little bit more about the energies and conservation of energy in a minute. In the middle here, you have your general reference to the spring forces, F equals negative kx. That's Hooke's law and elastic potential energy. Okay, and then conservation of energy over on the right side. Power. Power, whenever AP is asking about power, rarely do they ever say power. They usually talk about some rate of joules. Rate at which joules are expended, rate at which joules are dissipated, any rate at which work is done, or rate at which energy is dissipated, or whatever, that is dealing with power. So sometimes the key is just recognizing that it is power that they are asking you to be able to find. Now, let's talk specifically about graphs here for a second. If I have a force versus displacement graph, whatever that shape may look like, you have two interpretations here, slope and area. Slope, rise over run, change in force over change in position. If you're dealing with an elastic substance, this is your spring constant. Area, that would be force times displacement. The area is equal to the work. So anytime you look at a graph, always look at slope and area. In this case, both of those have interpretations. Now, on our middle two graphs, I want to consider the example of dropping a ball from a height. Well, if you think about gravitational potential energy dropping a ball from a height, U is equal to mgy. So on the top graph, mechanical energy versus height, the total mechanical energy, because gravity is a conservative force, that total energy is going to remain constant. If we break that down, into elastic or into gravitational potential energy and kinetic energy. Well, the gravitational potential energy is a linear function of y. And so when you drop it from a height, you start from that maximum potential energy, and that eventually becomes 0 as you reach the ground. Kinetic energy, that's a 1/2 mv squared. Now, the kinetic energy is dependent on velocity. Well, in a mechanical energy versus position graph, you don't have velocity on there, but you know the total is going to remain constant. So your kinetic energy is going to start from 0, and it's going to increase to that maximum. If we, on the other hand, jump down to the bottom graph, where now I have mechanical energy versus velocity, when you drop that ball, you start with 0 velocity, so you have 0 kinetic energy, but now you're dependent on a square, and so I'm going to draw a little bit better curve there. This is where you're going to have a curved relationship with that velocity. Your total mechanical energy is still going to remain the same. It's still going to remain constant, but your kinetic energy is going to be directly proportional to a square. Your potential energy starts at a maximum, but now when you're considering the relationship to velocity, velocity is not in mgy. And so based on the total being constant, then you're going to have, having trouble drawing lines here today, you're going to have a curve downward to 0. Okay, so it's important when you're looking at a graph, you recognize what is on the axes. Your total mechanical energy stays constant in either case. But if you're dealing with a function of position, you're dealing with linear because gravitational potential energy is linear. If you're dealing with the function of velocity, kinetic energy is proportional to the square of the velocity, so you get a curve for the kinetic energy and a resulting curve for the potential energy. Now, one last point I wanted to make on graphs over here on the potential energy versus position graph. If we have a graph here and we consider the slope, change in energy over change in position, okay, or du dx, the negative, the opposite of that, is going to be your force. We said work was the integral of f sub x dx. If you're going to change the energy, that becomes a negative integral of f sub x dx. So when I remove the integral, this becomes a differential chunk on the left side. And so my force is the negative derivative of the energy with respect to displacement. In other words, on this graph up here, the slope of this tells you what force is acting. That can help you in interpreting a graph and can sometimes be a quick, easy way to be able to get to the force. Now, let's consider conservation of energy. Your condition for mechanical energy to be conserved, only conservative forces are acting. Remember, we did 2 different tests to check for conservative forces. First of all, if we had a closed path, on any closed path, the total work done by the force is going to be 0. Okay, if I pick an object up from the desk and set it back down on the desk at the same location, the total amount of work gravity does on that object is 0. Conservative force, closed path, total work is equal to 0. If it was a closed path and our force was friction, if I slide an object in a circle around a desk, I'm going to do work the entire way and I'm not going to get a 0, so friction is not a conservative force. Second test, path from A to B. So if I go from location A to location B, if this is a conservative force, the total amount of work I do is going to be constant, no matter whether I take a nice direct route or I take a somewhat less than direct route. If you lift an object up vertically from a certain height to a second height, it doesn't matter if you go vertically upward or if you go diagonally from through the same changes in height, the total work done will still be constant. So, conservative forces are acting. Our conservative forces, gravitational force, elastic force, and also as we got into electrostatics, that electrostatic force is also a conservative force. So kind of embedding that into the whole idea. If you have identified that a conservative force is controlling the motion of what is going on, then basically you can interchange any of these different energies. Our linear kinetic energy, our rotational kinetic energy, our gravitational potential energy, and our elastic potential energy, and then also if we get into our electric potential energy. So then basically our joules remain constant, and so we can say E1 is equal to E2, E being mechanical energy. The total number of joules I have at one instant match the total number of joules I have at a second instant. Sometimes it's very important to identify where your U of 0 level is if you're dealing with gravitation, because then your heights are going to be measured from that location, but you're just flip-flopping joules from one to the other. If you have a non-conservative force acting, so if I have friction acting as I move my object from point A to point B, then I'm going to have my potential energies and kinetic energies initial, my potential energies and kinetic energies final, but then on the initial side, I will also have a work term. Work done by dissipative or non-conservative forces, work done by other, like applied forces. As long as you put it on that initial side, then the dot product in F dot dx will give you the right positive or negative sign to whether that work is being done to steal joules from the initial so that less are left from the final, or whether that work is being done to add joules so that more are left in the final. Okay, so you can still use conservation of energy mathematically if you have dissipative forces. Ponder physics.